Hi everybody. In this lesson we want to talk about synthetic division and also something called the remainder theorem, which is a way that you can evaluate polynomials using synthetic division. Alright, so let's start with this example here. We have a polynomial p of x given by this formula, and I'd like to divide that polynomial by x plus 1. So you remember that we use for the synthetic division the coefficients of the polynomial, 1 minus 3, 1 for x squared, 1 for x, and negative 6 for the constant term. I put a little box over here, and what goes in this is the value of k when I divide by x minus k. So in this case I would have to think of this as x minus a negative 1, so my k value is negative 1, and that's what goes in this little box right here. Okay, so I leave room for a row of numbers. I bring the 1 down. Negative 1 times 1 is negative 1, and then add these down. Negative 1 times negative 4 is 4, and add those down. And negative 1 times 5 is negative 5, and add those down. And then negative 1 times negative 4 is 4, and add those down. Okay, so when I divide this, I've got that p of x divided by x plus 1 is going to equal, well, let's see, I started with x to the 4th, and when I divide by x plus 1 I'll reduce the power by 1, so this is x cubed, and this is x squared, and this is x. This is a constant, and that's my remainder. So I've got x cubed minus 4x squared and plus the 5x minus 4, and then I could write the remainder over the divisor. Okay, so when I divide that out, I get this. All right, now what I want to do is I want to consider the same polynomial, and I'd like to evaluate that polynomial at negative 1. You might just notice that negative 1 is the value of k that we had up here. Okay, all right, so if I evaluate that in the way I'm used to doing it, p of negative 1, well, I'd have negative 1 to the 4th power minus 3 times negative 1 cubed plus the negative 1 squared plus the negative 1 minus 6. Then I have to simplify. So that's going to give me a positive 1 here, and then this is minus 3 times a negative 1, and then I'll get plus 1, and then the negative 1 minus 6, that's a negative 7. So what do I get here? I get 1 plus 3 minus 6. When I do the 1 minus 7, that'll give me minus 6. And so that gives me, let's see, oh, that's negative 2. Okay. Now I also want to evaluate it in another way that's going to help us understand what we mean by the remainder theorem. So notice from what we did up above here, if I were to go and check my result when I divided, assuming that I didn't make any mistakes, then I know that my dividend, right, this that I was dividing by, has to equal your divisor. I was dividing by x plus 1 times my quotient. Now here's my quotient right here that I've written right here. So that would be times x cubed minus 4x squared plus 5x minus 4. And then remember, you also have to add in the remainder. All right, so if I were to multiply all of this out and then add in the negative 2, that will equal my dividend, the original polynomial I started out dividing by. Okay, well, notice then that instead of writing the polynomial this way, I could also write it this way. This is just another way of writing it. Those are equal. But notice that when I plug negative 1 into this form, I'm going to get negative 1 plus 1, and that we know is 0. And so I really don't have to plug negative 1 into any of this. So that actually represents a huge savings of work that I would have to do. I can just say I don't care, whatever that is, because when I multiply it by 0, it's going to give me 0, and I'll just get the negative 2, which is the remainder, and you notice those are the same. Okay, so that leads us to the remainder theorem that says this. For any polynomial, p of x, if I want to evaluate that polynomial at k, that's going to be the same thing as the remainder of when I divide the polynomial by x minus k. So now to find p of k, you can do one of two things. You can either plug and chug, like we've always done evaluating a polynomial, or we can divide the polynomial by x minus k and find the remainder. Now it turns out, even though this is kind of new, that typically it'll be much easier, at least if you're doing it by hand, to divide by the polynomial and simply find the remainder. So let's do one more example of this to illustrate the process. Suppose my goal was to evaluate this function at -2. All right? So if I was to plug -2 in here by the old plug and chug method, then, and -2 is not a very big number, you know, -2 to the 4th power, and then multiply by 3, and -2 cubed, and multiply by 8, and combine them all together. All right? Well, what the remainder theorem says is that if I just divide by x minus a -2, x minus k, so notice that the -2 is going to go here in the box, I'd have 3x to the 4th, 8x cubed, 2x squared, minus 7x, and then minus 4. So leave a space for a row of numbers here. Bring down the 3, so let's multiply and add together, multiply, add together, multiply, add together, and multiply, and then add these down. All right? So when I divide this out, I'm going to end up with f of x over x plus 2 equals, I've got started here with x to the 4th, so now this is x to the 3rd, this would be x squared, this would be x. So I'm going to get 3x cubed plus 2x squared minus 2x minus 3, and then I'll have my remainder too. Now that remainder is actually my answer. If all I wanted was f of -2, that would be my answer right away, and I wouldn't have to go through this. But I'm going through this just to illustrate once again that instead of writing f of x this way, if I were to check my division, I would multiply the divisor, x plus 2, times my quotient, times the 3x cubed, plus 2x squared minus 2x minus 3, and then I'd add in the remainder. So instead of plugging -2 up here and having to do a lot of work, I can simply plug -2 in down here, which gives me 0 for this part, and then it doesn't matter what I get when I plug this in, so I don't have to plug it in. I can just say I don't care, and my answer is 2. All right, so again, if you know this ahead of time, which will always happen, then you divide, you can just immediately circle the remainder part, and that's the same thing as the value of the function evaluated at this number right there. Okay?